recap, you want to find an Eulerian path in the graph, which given a graph with these multiple parallel edges or self loops and normal edges, we want a path visiting every edge in the graph exactly once. And let's now revisit this question, but now we don't know the genome, right? So that is what we need to solve. When the genome is known, we build this graph, but if the genome is not known, how do you build this graph? From just the k-mer composition of the genome. Because the k-mer composition of the genome is what the sequencing machine will give us. And these k-length reads. And from the k-length reads alone, that is from the genome that we know of, how do we construct this de Bruijn graph? And then we can find the Eulerian path in this graph to reconstruct back the genome. Okay. So when the genome is unknown, how do you construct this graph? We have constructed this graph so far when the genome is known. Just to recap that, from the genome to the de Bruijn graph, we take the genome, we then split it into these edges where all the k was present in the genome, and then we started merging things and we got this graph, right? But now we are only given these k-mers from the genome. From here, we need to construct the de Bruijn graph, right? This is the one that the sequencing machine gives us, not the exact sequence of the genome. We want to go from the k-mer composition to the genome, which is unknown, right? So this is unknown now. We want to construct that. This is what is given as input from the sequencing machine, right? And then we want to construct a de Bruijn graph. So we want to construct a de Bruijn graph from here, right? And then we want to find an Eulerian path in this graph, and that should give us the genome. Okay, that is the strategy that we are going to use. So there are two steps now, from the reads to the de Bruijn graph, and then from the de Bruijn graph to the genome. So let's just look at the first step, from the reads to the de Bruijn graph. Okay, so from these reads, you can actually split every one of these reads, right, into the prefix and the suffix. So TGG will become TG and GG, right? And then you can then put an edge here and then label this edge as TGG, right? So every one of these reads can be split this way into two nodes and an edge. Then you can find all the nodes which are similar and merge them, right? That is precisely what we are going to do. Okay. So and then once you have that, you find the Eulerian path and you will get the genome. Okay. So that is what we will do. Okay, so I'm going to skip this one because we've already seen how to construct a de Bruijn graph and the genome is known. But let's just see constructing de Bruijn graph and the genome is unknown. Like I just said, we just take each of these and then split it into TGGT, the prefix and the suffix, and then label the edge with TGT. Similarly, this one we will say AT and TG, and then label this with ATG. Okay. So this is composition of this that we are given. So each one of them is a read. You just label those reads as edges, labeled edges, and then you label the nodes as prefixes and suffixes, right? And then you can start identifying things which are common and merge them. So there is an AT here, this one which is here, and then this AT is here. There is one more AT here. There are three ATs that needs to be merged, and some TGs which needs to be merged. This is a TG here, there's a TG here, there's a TG here, and the TG here. All of them have to be merged. Okay, so let's first merge A's. Okay, and then let's start merging these ATs, this TG, GC, CC, and so on. Okay, you start merging things, merging all the nodes so that there are no duplicate nodes. Okay, there can be duplicate edges. In fact, we want to preserve the edges because they are the k-mers, but there should not be any duplicate nodes. We are not done with the gluing yet because there is this, like I said, TG, TG, TG that is similar, and there is AT, AT, AT which are similar. All of them have to be merged as well. Okay, so let's just merge the AT like before, and let's merge the TG as before, and then we are done. One more, yeah, the GG is for the self loop. So in this particular case, we got the same de Bruijn graph. Okay, so the de Bruijn graph that is constructed from the genome is equal to the de Bruijn graph that is constructed from the genome composition. But I want you to think if it is always the case. Okay, offline you can think about for every genome, is it always the case that the de Bruijn graph that you construct from the genome, will it be exactly the same as the de Bruijn graph that you construct from the genome composition? But let's just move forward. Okay, we have a de Bruijn graph now that we can construct even if the genome is unknown. Now we need to figure out the Eulerian path, and that will give you the genome. Okay. So before going that, let's just summarize what we have learned so far. So de Bruijn graph of a collection of k-mers is represents every k-mer as an edge between its prefix and suffix, and then you glue all the nodes with identical labels. So that is what we have done so far. All right. And this can be written a bit more precisely, right, in the pseudocode format, saying that form a node for each k minus 1 mer from the k-mers. For each k-mer in k-mers, right, you connect its prefix node with its suffix node by an edge. Okay, so this is kind of converting this kind of informal gluing and other things in a more formal way. We are going to start describing this. Okay, now let's just take a pause and then see the different concepts we have seen. So from the Hamiltonian path, we came to the Eulerian path, and then we are just talking about de Bruijn. And so these are the people that I mentioned in the first slide, right? And where they are appearing. So the reason that de Bruijn features here is that he was studying a problem called the universal string problem in about 1946. So this is finding a circular string containing each binary k-mer exactly once. Okay, so you are basically given this, right? These are binary strings, and you want to come up with a larger string that will contain each of these binary strings exactly once within the larger string. Okay, and then de Bruijn solved this problem by constructing this de Bruijn graph and then finding an Eulerian path in this graph. Okay, and then that can be this is one such circular string where you can see that this is 0 0 0, so this is being covered. This is 0 0 1, so this is being covered. This is 0 1 1, this is being covered. 1 1 1, right, and so on. Everything will be exactly covered once as you go slide this 3-mer window along this circle. Okay, so here is 101 and so on. And then the way that you can represent it as a de Bruijn graph is by splitting each one of them into these 2 mers, right? Each of these k-mers into these 2 mers, and then labeling this 0 0 here, 0 0 1 here, and so on. Right? And this is how you construct this graph, and any Eulerian path through this graph, or actually an Eulerian cycle, because we are looking for a circular string. An Eulerian cycle is an Eulerian path that starts and ends at the same node, right? And so it starts at a node, it visits every edge exactly once and comes back to the same node. And so if you have such a thing, then you will, in this graph, if this graph admits such an Eulerian cycle, then you know that you can construct a circular string that will contain each of these k-mers exactly once.
Okay. We're always considering like k-mer with 3-mer, but it can be 4-mer and 5-mer. Like
yes, it can be 4-mer and 5-mer. So if it is a 4-mer, let's say I have 0 1 1 0. So then I will have my nodes as 0 1 1 and then 1 1 0, right? So this prefix and suffix, and then I will have an edge as 0 1 1 0. So
it's
the
minus 1. Like
yes. So this will always be k-mers, and this will be k minus 1 mers. This will also be, the nodes are always k minus 1 mers. Edges are always k mers. So it will work for any k. Just for simplicity, we are showing 3 mers here and 2 mers as the nodes. Yeah. So now this circular graph is, you start through this, and then you can go here, you can go here, you can go through the self loop, go here, go up, come down, and then come back to the 0 0 node. So that is exactly how you assemble the string back, right? So when you go here, right, this is actually 0 0 0, right? And then you go, because this is really 0 0 0, right? This is 0 0 1, right? So when you go here, then you are adding 1 1 here, right? So this is 0 0 0, then you have 0 0 1, and then when you are going to here, right, you have 0 1 1 here, so that is the 0 1 1, so you're adding this 1 here, right? So you're adding first these 3 zeros, then you have added a 1, you have added a 1 here, and then you keep on going to get this string. Okay. This is how it looks for k-mers where k is 4, right? So this is how the de Bruijn graph for a 4 universal string looks like. So it's called a universal string because it wants to contain all possible 4 mers in that single compact string. and so it's called the 4 universal string, and this string is called this 000111101 circular string is called the 3 universal string because it contains all the 3 mers in it. But then does it have a 4? I mean, is there a 4 universal string? Does it exist? That is equivalent to asking whether this graph admits an Eulerian cycle or not, right? If there is an Eulerian cycle in this graph, then there is a 4 universal string. If there is no such cycle, then there is no 4 universal strings. Okay, so that is the kind of problem that De Bruijn was interested in, and he was using this concept of De Bruijn graphs to answer that question. And so the natural questions are: does it have an Eulerian cycle, and if so, how can we find it? Right. So those are the natural questions here, and that is where Euler's theorem comes in. So we again, like from Hamilton we went to Euler, from Euler we went to De Bruijn, now we are coming back to Euler. And then so Euler actually gave this very nice theorem that says that when will a graph admit an Eulerian path, and if so, how do you find it? Okay. That's what we are going to illustrate in the rest of the in the next set of slides. Okay, we'll go back to the Eulerian problem. We are given a graph like this, and we want to know whether an Eulerian cycle or a path exists in this graph. So what is your thinking about it? So can you find an Eulerian cycle in this particular graph? You can visit nodes more than once, but every edge you have to visit exactly once. So far I can see that you're trying, but maybe not a solution yet. Let me also try. So maybe I'll start from here. I'll go to here. I'll go here. Then I will go here. I'll go here. I'll go here. But I'm stuck here. This edge is not being covered, right? Maybe I'll try one more. Maybe I will go from here. I'll go here. Here. Again, I'm missing one edge. This edge is not being covered. And so it's not just you and me. Um, if you keep on trying it for forever, right? I mean, there are many combinations, yes, that you'll have to try. But if you keep trying that, you will see that you will always be stuck. Okay. And then Euler came up with a characterization on which graphs will admit Eulerian paths and which ones don't. Okay. Maybe you have gleaned some things that even an odd degree, right? So if you have an Eulerian path, if you go into a node, unless it is the first or the last node, you'll have to come out of the node through a new edge. So every edge, every node that is not the beginning or the end should have an even degree, should have an even number of edges incident at them, right? So for instance, this blue node, if you go into the node, you will have to come out if this is an intermediate node. If it is a beginning or ending node, only for those two nodes you can allow exceptions. You can start and then you can go to all the other nodes and you can end at some other node. You don't have to come out of the node if you enter the node. But every other node in the middle, if you enter through an edge, you have to exit through a new edge that has not been visited earlier. So that will argue that if a graph admits an Eulerian path, except for the endpoint nodes, all the other nodes should have even degree, meaning that they should have even number of neighbors, then, right? Even number of edges that are incident to them. But what Euler showed is also the converse, right? So basically, what we are saying here is that if G admits Eulerian path, then it implies, in this particular case, I guess we are also talking about the cycle problem, just to keep things simple. So let me also change it to a cycle. So if G admits an Eulerian cycle, meaning you start at one node, you visit every other node, every other edge exactly once, and then come back to the same node. Okay. If that is the case, then every node in G should have even degree. Right, because if you enter a node, you will have to exit the node through you cannot reuse the same edge again. So it will have to be through a new edge, and then so every time you enter, you have to exit, and so there is always pairing of the entering and the exiting edge, and so every node will need to have a even edge. Okay, So here there are multiple cases where the edges are not even, right? So here you have 1, 2, 3, 4, 5. So this is odd degree node. The degree is 5. Here you have 1, 2, 3. The degree is 3, right? There are 3 edges incident here. So
have 3, like 5 and 3.
yeah, so there are basically 5 and 3, right? So if we ever need to hope to find an Eulerian cycle, you need to have at least all of these should have even degrees, right? But what Euler showed even is this reverse direction. This direction may be easy to see, but this direction is you need to show this is not trivial to see. But he was able to show that. I mean, we can still argue that. So if you have a graph where every node in the graph has even degree, then Euler argued that or proved that there will exist at least one Eulerian cycle in that graph that always admits an Eulerian cycle. Okay, this is not trivial, but it can be seen. We will see it in the next set of slides. By actually, he gave a constructive proof, meaning that it will actually give you an algorithm that will construct this Eulerian cycle given a graph where every node has even degree. Okay, and so that is what we will see in the next set of slides. Okay, so a graph is Eulerian if it contains an Eulerian circle. Is this graph Eulerian, right? So we are asking this can never be Eulerian, right? Why is that? This particular graph can never be Eulerian. It can never contain an Eulerian cycle.
It has like more than like and like odd edges.
Odd edges, and also very particularly if you enter into this node, there is no way you can get out, right? So you cannot start there and end there, or you cannot start somewhere else and go there and then come back to the starting node, right? That's one case. And then here is another case again. If you start from this node, there is no incoming edges, right? So you will always leave, and so this is also not Eulerian. And this seems to be Eulerian, so you can go like this. Oh no, actually not. Yeah, because for this node again,
Like
the incoming and the outgoing edges are not matching
like
up.
Odd edges also.
Yes. So you can kind of do this, but then these edges are not covered. Right. So all of these graphs are not Eulerian. There is one in and two out, right? So you can never kind of enter the second time, or you can't use both of these out edges. You can only enter once and then use only one of the outgoing edges. Okay, and so this is a directed graph. So when I meant in the previous slide that there is for an undirected graph you should have even degree. In a directed graph, the equivalent notion is that the number of the number of incoming edges has to be equal to the number of outgoing edges. So for every node, you need to have in degree to be equal to out degree. Then a graph is called balanced. So this graph is not balanced because there is one incoming and two outgoing, right? But if you have the in degree equal to out degree, then it's called balanced. And here, for instance, in the 4 universal string, right? So we can go back to De Bruijn. Is this balanced for every node here, right? So you have two incoming edges here, and then you have two outgoing edges. So this is 2 in and 2 out. Can look through every node here, everything will have 2 in and 2 out. So this graph is balanced actually. This De Bruijn graph for a 4 universal string that we are checking is balanced. So then this gives us hope that there is a 4 universal string if we can find an Eulerian cycle in this graph. All right. And so this is this one part of the theorem that I said. So a graph G has or admits an Eulerian cycle implies that the graph G is balanced, in degree equal to out degree. But the question is, what Euler showed is that every balanced graph is also Eulerian. Every balanced graph, so this is the one that Euler showed again. Both of them Euler showed, but this is the harder part of the direction. So this one is you can see, easy to see, but this one is also the other non-trivial part that Euler showed, that if G is balanced, then it will admit an Eulerian cycle. Okay, doesn't necessarily have to be the case, but it turns out to be the case. Okay. And of course, there are some criteria that you cannot have graphs like this. Let's say you have graph like this, you have 3 nodes and then another 3 nodes which do not talk with each other. This is the full graph. Let's say this has 6 nodes and then these 2 cycles with 3 edges each. Then you cannot start with one node and then come back to the same node, right? So you need to also make sure that the graph is strongly connected. meaning that from every node you can follow the edges and reach every other node. Okay, so if you allow this and this, right, and then you probably also need to add something like this to balance things out. Then this will become balanced. Okay, everything else 1 2 1 2 1 2 1 2 1 2 1 2 1 2. Yeah, this is balanced. So you need to have you need to be able to be strongly connected. So every balanced and strongly connected graph is Eulerian. Okay, so that is what he was able to show. And how do we prove this? So Euler was a genius at that time. Without any other help, he knew it. But then now we know that this theorem is true, so that makes it easier to come up with ways to prove it. So we can use the ants to prove it. So we can think about an ant trying to follow along this Eulerian cycle, right? So let an ant randomly walk through the graph. The ant cannot use the same edge twice, right? Because each edge has to be used exactly once. It leaves a scent so that it marks edges that are visited, and it wants to use a new path, new edge each time. Okay, we can start the ant at any place. Okay, it doesn't matter. So we can start it at any node, and then if the ant was a genius, it would have figured out the Eulerian cycle in the first attempt. Okay, it'll go here, it'll go here, it'll go here, 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 and here. Okay, so and you will be done, right? That you have found the Eulerian cycle. Okay, but of course the ant may not be that much insight to choose the right edge at every step, right? It may choose something else also. We may not be also starting at the right node, but in this case, I mean, every edge touches every node, so you can start at any node. But still, the decisions at each edge that you're going to make, you need to be intelligent to make that. A less intelligent ant would do more like this, right? So it may arbitrarily choose a particular choose a particular edge to start. So it just goes here, goes here, goes here. And can it get stuck at all? So that's the first question to ask. Can this ant get stuck for a balanced graph? You start and then you choose one outgoing edge, and then you have come here. So this is the starting point. And you choose an outgoing edge. You go here. You go here. You go here. Is there any possibility of getting stuck at any node? I mean, currently we are not stuck. There is still outgoing edges, but can it get stuck at all? And if so, at what node will it get stuck? So now there are two paths to go, right? So it can go either this way or this way, right?
If it goes this way, it will get stuck.
Yes, exactly. Yeah. If it goes the other way, it won't get. I mean, it may still get stuck later on, but at least not in the very next step, right? So let's just say if it gets stuck, okay, and if it gets stuck, it can only be at the starting node because every other node is balanced. If you enter, you have an edge to leave, right? You use up one edge in entering, you use up one edge in leaving, and the graph still remains balanced even after you remove the edges that are already visited, right? And so you come back to this original starting point, and this particular cycle is good that it visits these edges, but it's still not Eulerian. It's not using up all the edges, but it's good in the sense that we have come back to the starting point and we have a cycle that is good, and we are using up every edge only once, right? And then the other edges, there are still some edges. So can we enlarge this, right? So if we have not found the correct Eulerian cycle, then you can argue that there is at least one node in this green cycle that will have some uncovered edges. So now what I can say is that in this green cycle, right, there is always at least one node which will have unvisited edges. Because if all the edges are visited, then you will be done with the problem. You would have found an Eulerian cycle by now. If because we have not found it, we are stuck somewhere and there are still some uncovered edges. At least one of those edges should be incident at one of these nodes. Okay. So instead of this red node, then we can start at that node which have uncovered edges and then repeat the process. Okay. So let's start at a different node in the green cycle. Okay. I mean, there are other ways to solve this using backtracking and other things, but let's say the ant is just less intelligent. It doesn't want to backtrack and do other techniques of solving algorithms. We want to just look at it in some form of an easier decision that it can make. Okay, so let me just start with a node with still unexplored edges. Okay, this is one particular node with an unexplored edge. Then from here you can start to see if you can form another cycle that starts at this red node and ends at this red node. Okay, so starting at a node that has this unused edge, now we are going to traverse, right? And let's see.
If we can go back, there is another edge.
Right, so you have now gone from 1, 2, 3, 4. Now you can take the unvisited edge, right? So you can go through this blue edge, and then you can go through here, you can go through here, you can go through here, and then you stop here, you are again stuck. And then if you are stuck and there are still some unvisited edges, you can still go, you can change the red node to something else, right? So you now have this ordering. You go through 1, 2, 3, 4, 5, 6, 7, 8.
Instead of like 6, it can come over here.
Yes, you can choose any one of these three nodes, either this node or this node or this node.
This and this. It will be complete, even if it's starting at this edge.
Exactly, yeah. So that is exactly what we are going to do. Now we can move this red node to one of these three nodes, right? So either this A, B, or C.
From this red node, if we stick to this red node, still it can be completed because from 6 it will come down.
Yes.
Then this side, right hand side.
Yes.
Take the above one, that the curved
one. True. Yeah. So you are right that we can go through this way, and then this way, right? So that can be done, but that is called backtracking. Right, we constructed a solution and then we now backtracked and figured out a better solution. That may be harder for the ant to see with our global picture. We are able to see the ant is just moving around locally. It is seeing what the edges are, which is unvisited, and so on. Right. So instead of that, right, we can do the same local picture, which is. So let me remove that thing. We can make the red node one of these three other black nodes. All right. So then starting at a new node again you can kind of follow these blue and green edges to make a larger circle and go through this 1, 2, 3, 4, 5, then add this edge 6, 7, 8, and then you will go through the other unvisited edges. So this will be this orange one, this one, and now voila, you have proved Euler's theorem, in the sense that there's still some formal arguments missing, but this is a ant's way of proving the Euler's theorem. But I encourage you to write it down formally, right? So we may have an assignment problem about that. So this is the kind of the main idea is that you start, you have a graph, you start at some node and then you make some arbitrary decisions and then you will come back to the node, right? And then you will know that there is at least one other node which has unvisited edges, and then you just start from that node and then you explore some other cycle and then you come back to this, right? Maybe I should have used a different color. Let me use the second one. Will be you start at some unvisited node and then you kind of go on, you visit some more edges and then you come here, right? So now you have cycle 1 that you have, which is this cycle 2 you have, and then the cycle 1 was the red one. This is your cycle 1. Then you can know that you can merge both of these cycles into a larger cycle. So that's how you enlarge the current Eulerian cycle, two of these Eulerian cycles into a larger cycle. And then you keep on repeating this process. So now all of them together will be one cycle. So you can start from here, you can go along like this, you can go, you can start from here, you can go along like this, and then at this point you will go along like this. And then you come back to your red cycle. So both the red cycle and the green cycle can be merged into this one big black cycle. And then if there are still some things that are missing, right, maybe there are still some nodes here and then some edges which are missing, then you can also go cover it and come back, and then you can merge this blue and the black cycle, and so you can keep on enlarging the cycle until you cover all of the edges, okay, exactly once. Okay, so with that kind of an informal proof of the Euler's theorem, let me just, how will you try to prove it formally or to code it up formally, right? You use something called a pseudocode, right? You have seen it in your earlier classes, right? So you form a cycle by randomly walking in the balanced graph, avoiding already visited edges. While the cycle is not Eulerian, you select a node new start in the cycle with still unexplored edges. That was the one that was here initially, right? And then you form a new cycle, cycle prime, by traversing the cycle from the new start and randomly walking afterwards. And then you just enlarge, and your cycle prime has now been merged into the older cycle. And you keep on repeating this until you have covered all of your edges. Okay. And similarly here you can show the same thing, that this 4 universal string exists by constructing an Eulerian cycle in this particular graph. Okay. So now we have set up all the computational and the algorithmic framework necessary to finally come back and solve the problem, right? There is this notion of read pairs that adds a little bit of complexity to this issue, but so far what we have seen is this summary of so far what we have seen is that we have taken the genome, this unknown genome, and translated it into this k-mer composition, which is what the sequencers will give us. And then from the k-mers, we have now reconstructed back the genome by constructing this de Bruijn graph and finding an Eulerian cycle using this local ant algorithm, right? So there are some formal details in terms of the proof of the Eulerian theorem, and then how you actually convert this pseudocode into a actual code. Okay, that would be one of the programming assignments, that you can use your data structures that you use for representing graphs, and then implement each of these steps as some kind of operations on that data structure, and then you will be able to construct a graph, a genome, out of the de Bruijn graph from the k-mer composition of the genome. Okay.